All good? Hello, everyone. Thanks for coming. So a little bit about me first. My name is Vittorio. I'm a developer at Bloomberg, and I consider myself a modern C++ enthusiast. I've spoke at various conferences like CPPCon, C++ Now. I create video tutorials and articles about various topics that always revolve around the usage of C++. And I have a few open source libraries, games, and other small projects that you can find on my GitHub. So today we're going to talk about variants. I'm going to assume that you have an idea about what variants are, but in any case, we're going to have a brief overview of variants at the beginning. So how many of you are familiar with the concept of a variant? Nice, that's really good. So first we're going to take a look at variants and why they're useful, then we're going to take a look at visitation, and then we're going to take a look at recursive variants. Disclaimer, this talk is very code heavy. We're going to implement things as we go along. So feel free to ask questions at any moment, because it will be very important to understand every step that we take to implement our final result. So let's begin taking a look at variants. We'll see what variants are and the use cases. Various implementation of variants that you can find today, and then we'll take a look at std variant, which is standardized in C++17. So to understand variants, I like to use an analogy that begins with structs, then moves on to enum class, and then finally to variant. So since it's very early in the morning and we all want to wake up, I'm going to ask you, what is a struct? Who can give me a definition of a struct? Yeah, product type is a really good definition. If you wanna be, if you wanna put it in layman terms, you can say that a struct is simply something that models aggregation of types. So in this case, we have this point struct, very simple, and it has two integers. So we can say that a point is an int and an int. What is an enum class? Sorry? Aggregate, in my opinion, is something that tells you that you can have multiple of them at the same time. I like to use the word choice. So I like to say that enum class is a choice between values. For example, a traffic light can either be red, yellow, or green. So if we follow this kind of analogy, then a variant might be defined as a choice between types. So this is a very contrived example, but let's say we want to model the state of our oven. It can be either on or off. And in the case of the off state, we have no additional variables. Or in the case of the on state, we need to specify a temperature. So in this case, you can see that the oven is either off or it's on with a specific temperature. So you can think of this as a generalization of enum, well, where all the possible states can contain substates and be arbitrarily complicated. So this is a very small table that might help you see the various analogies. So a struct is a product type, and if you're not familiar with the term, it just means that the possible number of states that a struct can have is the product of all the states of its members. And it models an aggregation of types. Enum class is a choice between values, and variant is a choice between types. And some type means that the number of possible states is the sum of the states of all the possible members. So I like also to have an analogy with unions. So you can think of variants as type-safe tagged unions that do not require all the boilerplate that all system unions require. And they automatically deal with construction and destruction of types for you, and also immensely increase safety. So these are claims that need to be kind of verified. And what we're going to do is simply use an example to see how variant makes it better to model some types compared to union. So this example will be like this. We will have this shape, some type. So it's a choice between types, which can be either a circle or an axis-aligned bounding box. That's a rectangle, basically. And then we want to define an area function that, given a shape instance, calculates and returns its surface area. So this means that the area function will have to switch on the real type of the shape. And then, depending on whether or not it's a box or a circle, it will evaluate the area through a different formula. So graphically, you can think about a shape being either a circle with a radius or a box with a width and a height. So we will start modeling this kind of structure with a traditional tagged union first, and then we'll compare it to variant. This is how I would write it with a traditional tagged union. So first thing you'll notice is that we need this kind of enum here that represents all the possible types that our shape can actually model. So it has to have a value for circle and a value for the box. Then we need some sort of wrapper shape which contains the enum, and this is basically the currently active type of our shape. And then an union that contains a struct per type with the state that corresponds to that specific shape. So in this case, we will have a struct for the circle, which will have a radius, and a struct for the box, which will have a width and a height. And this is just the definition of the shape. If we want, so as a recap, we need an enum class with a value for every alternative, and by alternative I mean the subtypes that can be modeled by this variant, by this union, and a struct for every alternative that defines its state. So in this case, the radius or the width and height in terms of the box. And a union that wraps all the state struct types, because we need to reuse memory only for the currently active one. And an interface struct that wraps everything in order to avoid potential mistakes. And that was just the definition of the type. Now let's move on to the area. So if we want to calculate the area of a shape, we can start by taking a shape by const reference. And then we need to immediately switch on the type that the shape is representing at the moment. So it can be either a circle or a box, and we need a case for both of them. Then inside the case, we need to access the union, and then the struct, and then the value we want, and then we can finally execute the computation. And after that, we also need to make sure that we will do our best to catch possible mistakes when either adding or removing types, and we don't want to forget to adapt the struct. Adapt the switch to how our struct evolves. So as a recap, when visiting, and by visiting I mean finding out what the currently active alternative is and performing some action on it, we need a switch with a case for every alternative, and every case needs to access the relevant state by going through the union, and we also need some sort of an unreachable guard or something that will help us catch mistakes. So that was a lot of code, and if you're familiar with tagged unions, you've probably written something like that. Let's now see how STD variance compares. Sure? Oh, what did I do? OK, sorry.
The final fetch if you use plus alone? If we use plus alone, the compiler should tell us that the switch doesn't cover.
Yes. So the observation is if we use enum class, then this switch should tell us that we don't cover all the cases. But it's better to be careful, and if you have a default case here that might have a semantic meaning, and then you add something else that you want to cover separately, then it might not give you the warning as well. So it's error prone. You can obviously be careful and make it work. So for STD variant, the first thing you'll notice is that it fits on one slide, everything, not only the definition. So this small box over here is the entire definition of the sum type. We just need a circle struct that contains the radius, an AABB struct that contains the values for the box, and then we can say that we want a choice between them by simply defining a type def shape for STD variant between circle and AABB. And we get all of the boilerplate that we would have written for the union generated for us. And for the area, what we need to do is simply keep the same signature. So we take a shape as a const reference. And we'll see we use this STD visit over here that takes some visitor and the current instance of the shape. And this automatically dispatches to the correct function call depending on the currently active variant alternative. So if this shape S here is a circle, this visit function call is going to actually find out that the overload we're interested in is the one taken circle, and it will execute the correct computation. So we'll cover this syntax in more detail later. But as you can see, it's way more concise. So defining a variant type is trivial. all you need to do is basically list all the possible alternative types in the template parameter list. And visitation, like through std_visit or boost apply visitor, allows you easy access to the state you're interested in. So we don't have to go through the union or have additional boilerplate. And the visitor is checked to be exhaustive at compile time. So if you add a new type to your variant, if you remove a type from your variant, the compiler is definitely gonna inform you about that, which is really nice. So some examples of structures that you can model elegantly with variants are JSON, abstract syntax trees, state machines, and they're also really useful for error handling. This is a very, very, very simple example of how you could model JSON with a variant. So you could say that a JSON value is one of these at a specific point in time. It can be an object, array, string, number, boolean, or null. And then if you want to add serialization or deserialization, your interfaces will be really simple because you just return a JSON value or take a JSON value. And then inside those functions, you just visit on the current active alternative, and you do the correct kind of serialization. And another thing I really like is error handling through variants, because it gives you a sort of very rich, type-safe generalization of error return codes. So let's assume that we have this open file function here that takes some path, and we want to check whether or not we managed to open the file and get its contents, or we didn't find a file, or we had some invalid permission, we couldn't open the file. Then we can model all of these possible results as a variant. And this is really powerful because in contrast to exception or return codes, you are forced to deal with all the possible cases, and the compiler helps you with that thanks to the type safety that variant gives you. And you can also specify additional state that can tell you, in the case of success, for example, it will be the contents of the file. But if you add more complicated error conditions, you can have information about your error and handle it accordingly. So all these examples are using std variant, which is standardized in C++ 17. But there are several other implementations that you can use today in your code base. Boost variant is probably the most famous one. Then you have X variant, type safe variant, and Bloomberg BDLB variant. All of these are open source, and you can use them even in C++ 3 for some of them. So there are no excuses, just use variant. It's really powerful. And all these implementations differ from each other in very minor ways, maybe not that minor. So they obviously have different interfaces, but they also have different default initialization semantics. So some of them might initialize to the first alternative type. Some of them might require you to explicitly pass something in the initializer. Some of them might have an empty state. Some of them might try very hard not to have an empty state. Some of them deal with exceptions in different types, and some of them allow you to have duplicate types. So there are minor differences, but the idea is still the same, to represent this kind of sum type in a type-safe manner. The good news are that the visitation techniques that we're going to implement in this talk will be applicable to any variant implementation. So the ideas are the same. I'm actually working on a small library that abstracts away the chosen variant implementation and allows you to combine multiple implementations in the same project. And yeah, so the techniques we're going to use are not specific to std variant. But for simplicity, we're going to keep using std variant, which is probably the one that you'll see more in the future since it's standardized. And since we're going to use it, I think it's a good idea to take a quick look at its interface and see how you would use it in normal code. So std variant of some types can be constructed or assigned with any instance of the types or with any other variant instance that has the same parameter pack. So as a small example, if we have a variant between int and string, we can construct it with an int, and this will automatically set the current active type as int. But we can also assign it from a string, and it will automatically change its internal state. Likewise, we can construct it with a string, and we can assign it with another variant, and it will do the right thing. So it's very intuitive in its interface, and it doesn't require much boilerplate. Before visitation, we have also other ways of accessing the active alternative inside a variant. And those are std variant get and std variant getIf. And they provide a way of getting the value inside the variance. So in this case, we have a variant between int and string initialized with 1. So we can assert that the variant holds the alternative int. This means my currently active alternative is int. Then if we call get with int, we will make sure that it's equivalent to 1. So if for some reason you put the invalid type here, you will get an exception will be thrown. Also, there is another function called getIf, and this is more useful if you're not sure what's currently in the variant, because it will either return a pointer that's null pointer if the alternative is wrong, or a pointer to the value stored inside the variant of the type you specified. So this is a good way of accessing the variant if you don't know what type is actually storing.
Why it doesn't return the optional?
So the question is, why doesn't it return an optional? I think the problem there is that you don't want to copy the value. So you would have to return something like an optional reference. Yeah. But that's not supported by std optional. So, sure?
So if you did get if int, what's that going to return for the null case?
For the what, sorry?
Well, for the string, I can see it can return null pointer, but if you did get it of int,
yes.
what's the case where it wasn't there? Because if you return 0, maybe that's the value of the int.
No, so null pointer doesn't have the usual issues with null and 0. Null pointer is type safe, and it strongly means I'm a null pointer. It's not implicitly convertible to 0. Sorry? Can you repeat?
I think the question was, what does get return if it doesn't contain a null pointer? As a
Get throws an exception, unless I'm mistaken. Can someone confirm? Yeah. So basically, you should use get when you're sure what you want to access. GetIf if you're not sure and you want to check that the thing you want to access is actually the active one. But these methods are not actually that good, because they require you either to be aware of what the currently active alternative is, or you need some syntactical overhead, because you need to check that when you're accessing something through getIf, it's not actually a null pointer. And if you think about a variant which has a lot of types, you need like a very annoying set of if-else branches to cover those. And these reasons are why the standard libraries provide something called std visit, which allows variant visitation. And this is what we'll cover in part 2. So this is a recap of what we've seen so far. So variants are some types that model a choice between types, and they are safer and more expressive than traditional tagged unions. Things like recursive node-based structures like trees or ASTs, JSON, error handling, state machines are examples of concepts that variants can elegantly model. Also, std variant is standardized in C++17, and it is a vocabulary type. That means that you are encouraged to use that type in your interfaces, and that it should be something common between all programmers and easily recognized and easy to use. So any questions so far about variants? I hope you understand the concept. Sure? Okay, that's a good question. So how does variant deal with? Yeah, okay. So how does variants deal with memory? So you can think of variant as basically the same thing as a tagged union, but way safer and easier to use. So it's gonna the size of the variant is gonna be the maximum. The size of the biggest type that you can hold. So it's not gonna allocate. It's not gonna do anything. It's just a safer union. Sure. Yes. Sorry about that. Yeah, it's the size of the bigger type plus something that allows you to discriminate between the types, so some integer type or index type. Yes, there are some differences in implementation. For example, boost variant might allocate if you throw an exception, might allocate on the heap. But std variant, there's been a really, really long standardization process because they wanted to make std variant like as minimal overhead as possible, but also dealing with exceptions is hard. But it is guaranteed for std variant that it will not allocate on the heap. So you can use it freely. It's relatively cheap. Cool. So in part 2, we're going to deal with variant visitation. We're going to see what visitation is. Then we're going to look at something that I like to call traditional visitation. And then we're finally going to implement around lambda-based visitation. And this will require us to implement a way of overloading arbitrary function objects. So that might be useful even if you're not dealing with visitation. So let's first define this concept. So I like to think that visitation is an abstraction over accessing the currently active variant alternative in an exhaustive and expressive manner. And that will become clearer with an example. So when you want to visit a variant, you need some sort of callable object which can be invoked with every possible variant alternative. So if you have a variant of int and char, you need some visitor that has an overload for both int and char. So it needs to be able to handle all the alternatives. And the traditional way of creating such an object is by defining a struct with multiple overloads. So this is a very simple example. We have this myVariant type alias here, which can be an int, a float, or a double. And we initialize it with a float, and then we call stdvisit with printer and v0, which is our instance. And as you can see, printer is a struct, a stateless struct, that provides an operator call overload for all the possible types inside the variant. So what stdvisit is going to do is basically say, OK, what is the type active in this instance? It's float. Then I'm going to call this overload here and print the value with a suffix f. And the good thing about this is that this can be generalized to any amount of variants. So if you want to model some kind of collision resolution between circle and boxes, what you can do is simply have two instances of a variant that represents a shape, and then you can invoke stdvisit with both of them at the same time. And this is going to give you some sort of multiple dispatch between the variants that will handle all the possible cases. So as you can see, this is really powerful when you when you want to handle multiple dispatch between different types.
And if the variant contains types multiple times, is there a way to recognize which of the types you are lifting, or?
OK, so the question is if the variant contains a duplicate type. I'm not sure. There are differences between a std variant, boost variant. I honestly don't remember which one does which. But I would suggest, like, if you have a duplicate type and that hasn't been created through generic code because you want to generate a variant from some type list. So if you're actually writing a variant type and use duplicate types, then it's probably a code smell. You probably want some sort of strong type def there or do something like that. So if anyone has more information about that, yeah. Yes.
So if you've got, say, two strings, and you want to know which one it was, you can pass the index into that visit as well.
Yeah, the observation is there is an index method on std variant, and you can use that, but it doesn't help with visitation. The question was what happens with visitation.
You can pass it into the second argument. So there you've got v0 and v1, and you pass the index to the second argument.
Oh, OK. OK. So the observation is that you can pass the index as an argument to visit, and it's going to take that particular type in that particular location in the alternative list. Cool. By the way, you may have noticed that I have small links down here. And everything that has a code sample in the slides as a corresponding Godbolt link or Wonderbox link, these are online compilers. So if you want to look at the slides afterwards and maybe play around with the examples, you can just click here, and it will give you a compilable example of the current slide. So traditional visitation, in my opinion, has some shortcomings. Firstly, you need syntactical overhead because you need to define a struct with multiple operator call overloads. And if you see like this example here, most of this is boilerplate. All we care about is the logic here. Also, there is a lack of locality. You can usually define the struct near the place you're performing the visitation, but sometimes, for example, if the struct contains template methods, you need to define it outside the function where you're using the variant. So it can possibly be defined far away from the visitation site. So can we do better? And I'd like to take some inspiration from Rust, which is a language I'm very optimistic about. And this is how Rust deals with variants. So the first thing you need to notice is that variants in Rust are part of the language. So Rust provides language-level variants and language-level pattern matching. This means that the enum keyword in Rust is not as limited as in C or C++, but it also allows you to associate some state with the enum branches. So in this case, we have my variant, and we have 3 possible alternatives that are tagged with some name, like int tag, float tag, and double tag. And the int tag contains an int, the float tag contains a float, and the double tag contains a double. So this is how you define a variant in Rust. Then what we can do is instantiate a variant with the float tag. So this is actually a variant that's currently a float. And then we can use this match keyword over here to perform pattern matching over the currently active variant alternative. And as you can see, this is really nice. We just simply say, if this is an int tag of x, then simply print the value with the suffix I. So we can also the structure here. So I feel like this is very intuitive, and it's also very powerful because it allows you to specify patterns, but also decompose the patterns on the spot. So if you have like 2 values here, you can assign a name to both of them without needing additional boilerplate, like accessing the values. And it also allows you to specify an expression here with this arrow syntax, which is very intuitive and nice when you read the code. So if you compare it to C++, we need to define a struct here. We have a lot more boilerplate, and between the usage of the struct and its definition, there might be an arbitrary amount of code. While in Rust, the visitation is right next to where we're doing the pattern matching on the variant, and the boilerplate is minimum. So this is what I would like to achieve in C++. And this is what we will achieve by using lambda-based visitation. So as an overview of what we're going to do, we will have visitation done locally, so near the instance of the variant we're going to visit, by using a set of exhaustive lambda expressions. We'll aim to achieve a pattern matching-like syntax, and also aim to minimize the syntactical boilerplate that you get when visiting a variant. And obviously, and I hope this is obvious, we don't want to introduce any runtime or memory overhead. So this is going to all be metaprogramming magic and no extra overhead. And this is an example of what we're going to implement. So this is a variant that can be between int, float, and double, as before. We initialize it with a float. Then we call this match function here that takes a variant and returns something else that we can invoke again. And we invoke it with a bunch of lambdas, 1 per alternative. And the lambdas are the branches of our visitation. So this will do exactly what you expect. It matches the current active type inside v0, and then calls the corresponding lambda on the spot. And there's almost no syntactical overhead, and if we compare it again to the match keyword that Rust gives us, you can see how closely, how similar they look, because it's basically match something and then perform pattern matching on it. As a disclaimer, Rust match can be way more powerful than shown here. This is very, very basic usage, but the similarities still hold for variant visitation. So before diving into its implementation, let's look at an additional example. And this is another example of error handling, which I think works really well when you have this kind of local pattern matching, because you usually want to handle the error in different ways depending on where you're doing the visitation. So let's assume you have a request that can result in either a payload or an error. The payload is some data, and the error gives you a string that tells you what the error is. So you can model this kind of result over a request in a very nice and expressive way. Then you can use the match that we're going to implement to make some requests to a website, and then you can pattern match over success and failure, and you can nest them arbitrarily. And as you can see, since you don't have to jump up and down the source code, you can easily see the control flow and the logic of your requests all in the same place. That was for the examples. I hope you get the idea. And I actually think it's really intuitive, because you read it left to right, and you basically have your pattern matching and all the possible blocks that are going to be executed. And the way we're going to implement this is by creating a function match that will take nv variants and will return another function that will take nf function objects. And we want to take multiple variants here because we want to allow the multiple dispatch thing that you've seen before, like with the shapes. So conceptually, you call match with a bunch of variants, and it gives you a new function that you call with all the possible alternatives or combination of alternatives. And in order to create a visitor from the past function objects, so from this bunch of objects here, we need to build an overload set out of them. So if you remember, the struct is basically just a bunch of overloads. What we want to do is take some lambdas and build an overload set out of them so that we can use them for visitation. And internally, we will call std_visit with the variants that we basically bind here and the newly built overload set that we created over here. So the first problem is, how do we create an overload set out of the lambdas? So I want to do this like organically and see how you would think about it and how you would explore all the possibilities. And a reasonable way of starting is taking a look at non-member functions, so free functions. So let's say you have this foo function that's overloaded over float and char. And as you can see, if you call it with different types, you always get different results. So this is basic overloaded function. So can we generate an overload set out of free functions easily? Well, not really, because the first thing that blocks us is the fact that we cannot define them inside another function. So there is no way we can overload something here, because we cannot even define an overload inside here. So this doesn't really help. So since free functions don't help, we can take a look at function objects. So this is conceptually the same thing. We have a foo function object that contains two operator call overloads, and we can invoke it like the previous free function, but we need to instantiate it. And the good news are that we can define this inside another function. So we can arbitrarily nest function objects inside other function objects or functions. This is good. And also, we can compose this kind of function object via inheritance, which is the key that will allow us to implement arbitrary function object overloading. So in this case, if we have a foo float struct that has an operator call taking float and a foo char that has an operator call taking char, we can create an overload set out of them by creating some new struct and inheriting from both of them at the same time. One thing you also must use is this using declaration here that will bring both the operator call into the same scope as foo, so that the compiler will correctly perform overload resolution over both the base classes at the same time. And if you do this, you get the same syntax as before. So you're basically building your function object from a smaller function object using multiple inheritance and using. So one thing you might be wondering is, why do we need the using declarations? Well, if you don't have the using declarations and just use inheritance, you will expose the base classes operator call, but you will have an ambiguous error when you try to call the most derived function object. And this is because name resolution is performed before overload resolution, so the compiler doesn't know that it needs to overload all the base classes as operator call. You need to bring all of them into the same scope by using the using declarations. And if you want to try it out, there is a link here. Also, this is the relevant part of the standard, which basically deals with this issue. So we're back. We know how to build up an overload set from function objects, but we want to generalize it. And when we want to generalize things in C++, all we need is metaprogramming. So the first attempt is something like this. We have overload set that takes any number of function objects, any number of types of function objects. So what we do is try to inherit from them and then try to use all the operator calls by expanding the pack here. So if you're familiar with variadic templates, this should be fairly trivial. And what we can do is simply say, foo is a type alias for the overload set of the previously seen foo float and foo char. Then we instantiate foo, and we try to call it. Will this work? I hear not yet, not. So not yet is the best answer, because this will work perfectly in C++ 17, thanks to this proposal here, which allows pack expansions to be effective with the using keyword. But in C++ 14, this is an error. You cannot expand a pack in a using declaration here. And this happens because C++ 14 using declaration don't support multiple comma-separated items. So you cannot say something like this in C++ 14, but you can say that in C++ 17. Yeah, we might use C++ 17 for this, but even though SCD variant is standardized in 17, there are a lot of uses for variant in previous standards, and you can find really good production-ready implementations. So in order to be a little bit more versatile, I want to show you how you can build an overload set in 14, which is slightly more complicated, but it obviously allows you to use this kind of visitation even with boost variant or other implementations in your firm. So the problems are that since we cannot expand all the usage declaration in place, we can only refer to one of the base classes as operator call and introduce it into the scope of the overload set with the using keyword. So we can match only one of them. And there is no way of generating all the using declarations at once. So how can we work around these limitations? Well, the first limitation actually gives us an int. If we can match one of the base classes, we can basically match that one and then do some sort of recursion on the rest of the types. So as I just said, if we change our definition to match the first type and then the rest of the function object types, we can definitely say using operator call on the first one, because this is not a pack. But then we need to do something with the rest of the function objects. So we need to do some sort of recursion to bring everything into the same scope. And this is how it looks like. It's not very complicated once you see it, but when you think about it, it's slightly tricky to get right. So the idea is that the base case is a specialization of the recursive case, which takes any amount of function objects. And the base case is simply, given a function object, I just want to expose its operator. And that's it. For the recursive case, we expose the first function object's operator call, and then we use a recursive user declaration on an overload set of the rest of the functions. So if, for example, we have two function types, the first one will be exposed here, then the recursion here will hit the base case, and it will expose the other one for us. So this is what you need to build an overload set out of arbitrary types in C++ 14. Once we have that, we can try it out. And just to try it out at compile time, I decided to make foo float and foo char have a constexpr call, operator call. We can build an overload set out of them by specifying all the types in the template parameter list, and then we can static assert that it does the right thing. And this works well for function object types. But if we want to support lambda expression and automatically deduce the function object types, we need two improvements. The first issue is that lambdas are not default constructible. And I think that Louis wants to change that and wants to make lambdas a little bit more flexible, which is nice. But regardless of that, we still want to perfect forward the instance of the function object or the lambda we care about inside our overload set. So we need a perfect forwarding constructor. Also, we need to provide an overload interface, which is a variadic function template that can accept any function objects and will deduce their types for us, because there is no way of specifying the type of a lambda, and we obviously don't want the user to do that during visitation. So let's begin with the constructor. So in the base case, all we need to do is simply add this perfect forwarding constructor here. And what I'm doing is defining a templated constructor which takes a new type name by forwarding reference and forwards it inside our base class. So this is basically saying, I'm wrapping a function object. Please initialize me by perfect forwarding an existing one into myself. And please know that I'm not using tf ref here, because that wouldn't be a perfect forwarding reference. It would be an R-value reference, since there is no deduction, no template argument deduction happening. So to be as flexible as possible, you need a new type name here. For the recursive case, it's slightly more complicated, but it's not that hard to understand. So what we're doing is still initializing the first one, which is the one that we matched here in the first template argument by forwarding the first function objects. Then we're going to take a bunch of other function objects via variadic template here, still a forwarding reference. And then what we want to do is construct the base class with all of those function objects. So we have two ellipsis expansions here, one for the types of the base class. So as you can see, this matches this exactly. And then we want to forward all the other function objects into the constructor of the base class. So this parameter packs will basically be expanded in lockstep, and it will do the right thing. So once we have this, the last piece of the puzzle is some way of deducing the function object types via an extra function. And what we can do is define this overload function, which returns by auto, so it's going to deduce the type for us. And it takes an arbitrary amount of function objects by forwarding reference. It will create an overload set by removing the reference from all the function object types, and I'll get to that in a second. And then it will forward the values to the overload set as constructor. And here, we need to remove the reference because since this is a forwarding reference, there is a special rule in the language that says that when you pass an L value to a forwarding reference, its type is going to be deduced as tref. So we don't want the reference in the type of the overload set. We only want the concrete type without any reference. That's why we need to remove it here. You might have seen this before with decay, and the idea is the same, just removing the reference that can be added through perfect forwarding. So is everything clear so far? Nice. Sure.
Same as the posted overload?
Sorry?
Is this one the same or similar to the proposed STID overload?
Okay, so the question is this the same as the proposed STD overload? So there is actually a proposal to add this thing into the standard library, which will be STD overload. I think it's conceptually the same. It does the same thing. I don't know if it's implemented the same way. You can probably have a more clever implementation and more efficient compile time, but the idea is the same. So with everything in place, we can finally write this, which is really nice. We simply have auto O initialized by overloading these two lambdas, and then we can static assert that when calling them with different values, they're going to give us the correct result. And note that I can use static assert here instead of assert, because in C++17, lambdas are implicitly constexpr if possible. So this is a really nice addition that allows me to check more things at compile time. Completely unrelated, but it's nice to be able to use static assert here. So since lambdas don't have a type that you can refer to, we definitely need some sort of thing that deduces it for us. And overload is the function that does that. Now that we have a working overload set, we basically did most of the work required to implement match. So we can finally have this snippet compile and work after implementing some additional utility boilerplate. Let's do it. So if you remember, match will be a function that takes nv variance, so here, and then it will return another function that takes nf function objects here. And what it will do is basically bind the variance to something, wait to build an overload set, and when the overload set is built, do the visitation. So if we want to translate this conceptual idea to code, we will see that match will roughly look like this. So we will have this function that takes a bunch of variants, and will return another function that takes a bunch of functions. So this is the skeleton of match, and it's just there to tell you how to translate this idea to some possible implementation. It obviously doesn't do anything yet. So Since we have overload set and STD visit, the implementation of match is actually quite trivial. All we need to do is capture the variance by reference inside this lambda here that will accept any number of function objects. Then we need to deduce the type with decal type auto because the visitation might result in something that's not a value, so we don't want to accidentally copy it. We need to tell the lambda, please deduce the actual type of the visitation. Inside the lambda, we can build our visitor by overloading the function objects by perfect forwarding them inside the overload function call. And since we don't have the types here, since this is auto, we can simply use decal type here. And once we have that, we can call std visit on the newly created visitor. And we also want to pass the variance we've captured by forwarding them inside the std visit call. So this is all you need to implement match. Any question about this code snippet? Sure.
If you get some loop-only algorithm for the variance, should you also move them into the lambda?
So the question is, should you move the variance into the lambda instead of capturing them, right? By reference.
Forward them into the lambda.
So in this particular implementation of match, my idea is that you do the matching directly on the spot. So you're not using it in a carried way. So it's just like you match this variance immediately here. So there is no need to move them inside this, to move or prefer for them inside the lambda. If you wanted to do that, it might be useful if you want like to bind the variance and then visit them with different visitors all the time. But it's way more complicated because. And finally, once we implement match, the snippet here compiles and prints the value we expect. And you can try it out here. So as you can see again, I really like this. I think it's intuitive and nicer than having to build a struct. You just say match this variant and do something on the current alternative. And here's an example with multiple variants. So it doesn't look as ugly as you might expect. We simply match two shapes here in the first function call. And then we provide a bunch of lambdas that need to cover all possible combinations of the variant alternatives. So again, I feel like this is very intuitive. You just have two variants and then all the possible cases on the spot. And one more example with nested variants. So if we have, again, this is the most common example with a response that can either be success or failure. And maybe we have maybe our success and failure states are actually variant themselves. So we have like a tree of possible alternatives. It's still OK to read. There's slightly more boilerplate, but you can, again, follow the control flow quite easily. You can say, OK, match the response. If it's a success, what kind of success it is, and you match over here. If it's an error, what kind of error it is, and you match over here. So you can still follow it top to bottom. So as a recap, variant visitation works by invoking an overload matching the active alternative on an overloaded visitor function of function objects. The using declarations and inheritance can be used to create overloads of arbitrary function objects. So combining those two language features allows you to do that. And it's not only useful in the case of variant visitation, but I'm sure you can find other uses for it. Lambdas are just syntactic sugar for function objects. So all I said before applies to lambdas as well. And overloads of lambdas built on the spot can reduce boilerplate and increase locality when visiting variants. Now, I want to make it really clear that this is not an absolute substitution of the struct-based traditional visitation, because that's still really useful. Struct visitors can, in fact, contain internal state and provide a richer interface. So it might be a visitor, but also have methods on it. Also, they can be more easily shared and reused in a large code base. You don't have to copy-paste the visitation. You just have it in one place, and you reuse it throughout the code base. And they can also provide customization points. So you can think of some visitor, which is a struct, and maybe allows you to plug in some logic through a template parameter. My guideline is, if you decide to use this lambda-based visitation, do it only when your logic is simple and local. So it's very closely related to where you're visiting the variant. otherwise prefer struct-based visitation. So it's not an absolute alternative to it. Both of them have their own uses. Any question on part 2? Good. So match can be implemented in less than 40 well-formatted lines of C++ code. And if we use C++ 17, it's even less. So why is my talk 1 hour and 30 minutes long? There's a catch. And the catch is recursive variants. So we'll cover that with a brief overview of recursive variants. Then we'll see how we can visit recursive variants in a traditional manner. And then we'll see how we can implement recursive visitation with lambdas. And we're going to need a scary thing that's called the Y combinator to achieve that easily. So a recursive variant is a variant which can contain itself and can be used to represent recursive structures. So if you think about JSON, it is inherently recursive because a JSON object can contain other objects. And JSON is quite a complicated example to show on slides, so let's have something simpler. Let's say we want to represent arithmetic expressions, very simple ones, as a variant. And you might do this if you are trying to build up an AST for your own compiler or interpreter, whatever. So let's say that 5 is an expression containing a number. 9 plus 3 is an expression containing a number plus an expression containing a number. So as you can see, this is defined recursively on expression. And 1 minus 3 plus 7 is an expression of a number minus an expression of a number plus an expression of a number. So this is the recursive structure we want to implement with variants. This is a possible grammar. We can say that a number is an int. An OP, which is an operation, can be either plus or minus. These are like tag struct types. And expr can either be a number, this is the base case, or the recursive case is a number followed by an operation followed by another expression. So this is a fairly simple and limited grammar. And if we want to model this grammar like immediately in C++, what you would intuitively try to write is this code over here. So since a number is an int, we simply use a type alias. Operation can be plus or minus, so we just provide two empty structs, and we say that operation is a variant of plus or minus. So it can either be one or the other. And then we want to provide expression, which in the base case, it's a number, and in the recursive case, it's a number, operation, and expression. So we use a tuple to tie up these types together, and a variant to represent that we want to choose between the base case and the recursive case. This is very easy, very simple. It doesn't work because expr is not declared in this scope. And if you think about this piece of code, it seems weird because expr is here, so it should be declared, right? But conceptually, what you're trying to do is this. So when you define the tuple over here, you're like having a different type alias that's called rexpr for the recursive expression, and you're trying to use expr before it's even defined. So the compiler error makes sense. It's just harder to get because you're doing it on the same line. When we have this kind of issue in our code with structs or whatever, what we try to do is use a forward declaration to allow the compiler to see the name before it's actually defined. So could it help in this case? Well, it does fix the error we had before if we do something like this, where we forward declare the expr struct, then the recursive part, and then we define the variant inside the struct. So we're using this forward declaration here. It does fix the previous error, but gives us another one, which is invalid use of incomplete type struct expr. And this, again, makes a lot of sense, because if you think about the expansion of this recursive structure, you're going to put a tuple here, then another tuple here, another tuple here. So what's happening is that you're creating a struct of infinite size. And when you have that kind of issue, you know you need an extra layer of indirection. So this is what you have to do to avoid creating a struct with infinite size. So again, you have a forward declaration here, so you can define your tuple, which is the recursive case. Then inside the struct expr, which is the wrapper for the entire variant, you can define the variant inside, which is between a number, which is the base case, and a unique pointer of the recursive case. And this indirection here solves all our issues because it makes the size of the variant fixed, but still allows us to recurse through this heap allocation. So obviously, the size of any instantiation of a city variant must be fixed. It cannot be infinite. And recursive variants can be defined by using forward declarations and indirection. This is pretty ugly. There are ways to make this nicer with metaprogramming, but the idea is always the same. You need forward declaration, recursive case, and then some indirection. One thing we also need to do is provide a constructor to simplify the usage, because even if this is a recursive variant, we still want the nice syntax here that says an expression is 5. So what I'm doing here is basically saying in this wrapper expr that I need, because it was forward declared, please take any number of arguments and forward all of them to the variant. That's pretty much what it's doing. So it's just for nicer syntax and nicer usage. Once we have that, we can finally model our expressions as recursive variants. So in the case of 5, we can trivially say E0 of 5. When we have 9 plus 3, we can say expression E1 is make unique of 9 plus 3. And this is required because the recursive case is hidden behind a layer of indirection. So we need to construct a unique pointer or something like that. In expression E2, which is 1 minus 3 plus 7, what we can do is nest this arbitrarily, and we can say make unique of 1 minus make unique 3 plus 7. So this is going to build up our recursive variant. And there is some boilerplate, but you get the idea of this recursive node-based structure, which can elegantly model ASTs or expressions. Everything clear so far? So the problem is now, how can we visit recursive variants? In the case of recursive traditional visitation, we can use a struct with an overloaded operator call, and one or more overloads will recursively visit the variant, and one or more will be base cases. And by simply invoking stdvisit, it will just work. So this is how you would define something that evaluates our expression. We'll have a base case here, which takes a number and returns the number. So that's a simple, very simple base case. Then the recursive operator call will take a unique pointer of the recursive expression and name it x. Now here I'm using structure bindings to the structure the recursive variant type into its small pieces, because if you remember, this is a tuple. And if you're not familiar with structure bindings, it's basically saying, OK, give the first element of a tuple the name LHS, the second element OP, and the third element RHS. And once I destructure the tuple, what I can do is visit the recursive part, which is the right-hand side. I will just show you again the definition. So we're going to visit the right-hand side, which is the expression. It's the recursive part. And the visitor will be start this, because we want to recurse on ourselves. We want to visit the recursive part of the variant with ourselves, because we are the current visitor. And then I'm going to use match that we implemented before on the operation to either return the sum of the number plus the recursively visited number, or the subtraction of those two values. So this is not that bad. I mean, there is not much boilerplate, but for the sake of experimentation, we want to make this with lambdas as well. Before doing that, let's see some example usage. And in this case, we have the expression that we had before, and we simply call stdvisit with our evaluator, and we need to access the variant inside the wrapper by using underscore data or whatever your member name is. And you might be able to use inheritance here. There are various ways you can define a recursive variant when you have the kind of forward declaration and then wrapper definition structure, but I prefer to use an explicit member here. And I feel like we have all the shortcomings that we had in the non-recursive case. So the visitor has syntactical overhead, and it might be defined away from the visitation side. But we also have explicit nested visitation. And this requires calling SCD visit inside the visitation logic. This is not really a problem. But if you're working with multiple variant types and implementation in the same code base, you would need a visitor per variant implementation. What we want to do is abstract away the idea of recursively visiting something and just say recurse on this branch. We don't want to explicitly say SCD visit. That's like an implementation detail. So before diving into the crazy Y Combinator stuff, we can make a small improvement here. So you might have noticed that we are forced to specify the data member when using SCD visit. So let's just create a simple wrapper that does that for us, and I'll call that visit recursively. This is just syntactic sugar. And this visit recursively will take everything by forwarding reference, will forward it to visit, and in the case of the variants, it will forward the variant, but access the data member for us. So this is just syntactic sugar that allows us to avoid specifying data, data, data over and over. And this very simple change makes the code cleaner. As you can see, we can use visit recursively here, but this is still explicit visitation. And in the user code, we can simply say E0, E1 with visit recursively instead of accessing data. And this is useful if you decide to change your implementation from a member-based one to an inheritance-based one. You can abstract the idea of getting the nested variant into the visit recursively function. So we're going to implement lambda-based visitation now. Is everything clear about recursive variants? I can go back and review it. Are you totally fine with it? OK. So. OK. So let's go into recursive variant types with lambdas. The first thing I want to review is a recursive variant type. And again, I want you to be very clear on how this works. So this expr here had to be forward declared before because we need to refer to it in a recursive case. The recursive case is this tuple here, which refers to expr. And at this moment in time, expr is just an incomplete type because it's a forward declaration. Now we want to define the top-level variant, which is the recursive variant. In order to do that, we need to define it inside the implementation of expr. And the variant will be between the base case and the recursive case, which internally uses expr, which internally contains the variant. So this is how we achieve the recursion. So intuitively, with this recursive variant type here, we should be able to write something like this, because we have overload, right? So we can overload whatever we want. So we should be able to say auto-vis, that stands for visitor, overload onto this base case here and this recursive case. And when I want to visit recursively, I just say vis here again. So this should just, do the thing recursively and then eventually hit the base case. It should work. So does this work? Why?
Because basically the same issue, you have this not correctly defined it. Are using it.
Exactly. So as Arne said, this will not work because I'm trying to use this when I'm defining it. So the compiler does not know what to do here because it cannot even deduce the return type or anything. This is ill-formed. And the error we get is that use of this before deduction of auto. The issue is that the compiler is not able to deduce the type of the visitor inside its declaration. You need to wait until the declaration is completed. And the real issue, the real underlying issue here is that the language does not provide a way of referring to the current closure in a lambda expression. And let me explain that. So a lambda expression is just syntactic sugar for a function object. I hope everyone is familiar with that. So when you say something like return 0 into a lambda expression, you're actually generating a struct, which is anonymous, and it will provide an implicitly const qualified operator call that returns int because it's getting deduced by auto type deduction, returning 0. So this thing here is just syntactic sugar for this thing here. Sorry? Here, right? Yeah. I implicitly deduced it in the slide, but this is generated as auto. So inside the definition of a member functions, when we are in the context of a struct, we can refer to the current instance of the parent object by using the this keyword. So if we are like inside foo, and we have this kind of very stupid linear recursion, we can refer to ourselves by saying this. And this keyword here refers to the current instance of the struct that we're using. But inside a lambda expression, this has a different meaning. It does not refer to the current generated closure. So it does not refer to the struct that's been generated through the lambda expression. It actually tries to refer to the outer context. So you might have encountered this a lot when you try to using a lambda expression inside a class. When you use this inside the lambda expression, you are actually referring to the class which contains the lambda expression, not the closure itself. So if you try to do this, you will get this error because the keyword was not captured for this lambda function as it tries to refer to the outer context. So the issue here is that I have no way of saying, please refer to my own closure, to the lambda itself. I have no way of saying that. And there is an example in this proposal here, which unfortunately got rejected, that shows how in the future the language could allow you to refer to the current closure instance. And you might be able to do something like specify an identifier here between the capture list and the argument list. And then you might be able to use the identifier inside the body to refer to the current closure. So this is like a generalization of this keyword that you can give a name, and it will refer to the current instantiation of the lambda expression. I hope that makes sense. OK. So unfortunately, we don't have this. And this proposal here was actually for Y Combinator, and it got rejected. This idea here was just in the comments. So I would like to see a proposal that just covers this issue without any extra library feature inside the proposal itself. So I really want to have a recursive lambda. I really want to do it. So how can I do it without runtime overhead? You might know that if you want to define a recursive lambda, you can get away with a std function because a std function has a concrete type, and you can refer to it inside the body of the lambda. But you shouldn't use a std function unless you need the type erasure that it provides. It's not a lightweight wrapper for a function. It's a heavyweight wrapper for any generic function object that can be type erased. So what we want to do is find a solution that does not require runtime overhead. And the basic example is the factorial function defined as a lambda. So in this case, we simply have our logic here. The base case is when n is 0, we want to return 1. Otherwise, we want to return n multiplied by some magic here, which will refer to ourselves, and n minus 1. So we know that if we use fact here, it won't work because fact is not defined. If we use this here, it won't work because this refers to the outer context, not the body of the lambda expression. So we need an extra idea, a new idea to try to recurse. And what we might try to do is bind fact to itself and pass it as an extra argument in order to use it inside the body. It looks weird. So what we do is have fact. It takes an auto self parameter here. So it's taking itself as a parameter. We also need to have a mandatory trailing return type to help the compiler deduce what we're going to return. And once we do that, we can call n multiplied by self of n minus 1. And what this is doing is calling this function object that we passed with itself again and making progress in the recursion. And if we try to static assert it by calling with fact factor 3 to the expected result, it works. So this is how you define recursive lambdas without any extra cost. And great, it works, but I have to repeat myself like 4 times. I have to say self of self, fact of fact, which is very annoying. I honestly don't mind much about this because it's hidden in the implementation of the lambda, but we also force the user to repeat the name of the lambda twice on the call side. And that's really bad because you don't want to force the user to have repetition in the code base. So can we do anything about it? Yes, we can use the Y combinator. So if you're not familiar with this thing, it's a concept that's commonly found in functional programming languages. And it is a higher order function. So it's a function that takes other functions. And what it does, it can be used to implement recursion. So this concept here from lambda calculus allows us to implement recursion in languages that do not natively support it. And this will be our final result. So when we are defining fact, we will define it through a Y combinator call. And we will still have the auto self parameter here. But both in the implementation and in the user caller side, we will only have to repeat self once. And in the case of the user, we will only have to say fact of 3, which is the desired interface for the user. So what Y combinator does, it does the pass myself to myself recursive thing automatically for us. That's all it does. So even if you don't know its implementation, and as long as you remember this, what it does is simply prevents you from having to write this twice. It does the passing automatically for you. And I want to implement it. So let's start thinking about how it could work. So Y combinator can be thought of as a function template which accepts any function object f of arity n and returns a wrapper f prime around f which has arity n minus 1. And the arity gets decremented by 1 because one of the arguments of the wrapper is bound to the wrapper itself. So what Y combinator is doing is defining a wrapper that will allow us to recurse on any lambda, and it's binding the wrapper itself as its first argument of invocation. So it's doing the thing that recursive over for us. And here's the possible implementation. This was actually proposed to the standard library. It got rejected in the proposal I mentioned earlier. But this is a very simple implementation of it. So what you can do is define this Y combinator wrapper that wraps an arbitrary function object. You always want to perfect forward a function object inside the wrapper. So all of this is boilerplate. And the real interesting thing is the overloaded operator call. It takes any argument, any amount of arguments by forwarding reference, and then what it does, it calls the original function object by passing this by reference as the first argument. So we're passing the wrapper itself as the first argument of the original function object, and then forwards everything to the call. So conceptually, you can think of this as binding the wrapper to the invocation of the function object as the first argument. And this avoids repeating self-self or fact-fact when we're dealing with recursion. It's not trivial to understand. You need to think about the case and maybe expand it on paper. But if for the context of this talk, just know that it allows us to recurse without any extra syntactical overhead. And again, as we did for overload, we want something that deduces the type for us. Otherwise, it's annoying to write out. So what we do is Y combinator, get something by forwarding reference, and build up a wrapper by decaying or removing the reference to handle the forwarding reference case correctly. And then we forward it into the wrapper. Sure.
I was just wondering, is there a reason that you cannot use a deduction guide for that instead of using it?
Yes, so that's a good question. The observation was, why aren't you using a deduction guide for that? So deduction guides and template argument deduction for classes are new features in C++17 that basically remove the need of writing all this boilerplate thing that uses template arguments, because now template argument deduction for classes is allowed from the class instantiation itself. And yes, it would completely eradicate the need for this, but I want to be C++14 friendly for the talk. So that's the reason. Cool. So now that we have Y combinator, we can write this, which is a definition of factorial that recursively calls itself. And the code now compiles, works, and doesn't have any extra overhead. I have some benchmarks on my website of this thing versus STD function. And you can see that the generated assembly is significantly smaller, significantly, because a CD function is hard to optimize due to the type erasure and to the internal buffer. So you will get performance degradation with it. Well, this thing here, everything is templates, everything is inlineable, everything is visible to the compiler. So you can just reduce it as much as possible. Now that we have this, we can finally implement recursive lambda-based visitation. And what we'll have is the same pattern matching like syntax. We will try to minimize syntactical boilerplate, no runtime overhead, but we will also abstract the nested visitation behind a recurse call. And that's what I find interesting, because by doing that, we prevent exposing details about the visitation to the user, and we just say, this is the way you recurse. And this is what it will look like. So let's say that we have this expression here that's built recursively. Then we will have this match recursively function that takes a return type. I couldn't manage to have the return type deduced. It's way harder than it looks. So we know that this recursive visitation will return int. Then it takes a bunch of variants here. And then what you do, you provide your function objects, your lambdas, as you did for the non-recursive match. But every lambda you provide will take an extra parameter here by auto. And you can ignore it or use it to recurse. So this auto here will be provided by match recursively, and it will give you a way of performing the recursion inside the body of the lambda. So in the case of the recursive expression handling, when we do the match inside here, we can just invoke recurse with a recursive part, and this will deal with the horrible task of going through the generated overload set again recursively. So what I did is like create this function wrapper that allows you to recurse and pass it to the visitation itself. And if we try it out, it works as expected, and the code is even shorter. One caveat, this auto over here, I hate it because it's a base case. I don't want the auto there. I tried so hard to get rid of it. It's insanely hard. But now that we basically get how it works, so all you need to know is that this recurse is some magic provided by match recursively or make recursive visitor that allows you to do the recursion. And another thing that I forgot to mention, sorry, is that we will implement match recursively in terms of make recursive visitor, which is simply a way of providing an overloaded set that can also recurse on itself. And the way we'll do it is that we'll first have this function, make recursive visitor, that will accept a return type t as a template parameter, because deducing it is non-trivial, and I'm not sure it's actually possible. And it will take any number of function objects, fs, as input, and this will be the visitor branches, if you want to call them like that. So this is conceptually what it will look like in terms of interface. So as you can see, we take the return type explicitly and then a bunch of function objects. Now, you need to understand that since we want to allow recursion through an extra template parameter, through an extra lambda parameter in the function object provided by the user, all the visitors will have arity n plus 1, where n is the number of variants, but the extra plus 1 is this thing here that you can either use or ignore and allows you to do recursion. So all the lambdas that the user will provide will have an extra argument that will need to, that can be used to recurse. And the visitor is going to be used via visit recursively. So if we have something like an evaluator and an expression, we're going to use visit recursively to access the data member. So this is just a reminder of why we have this thing. It's just to abstract away the access of the data member. Therefore, the function object that we pass to visit recursively must have arity n, which is the number of variants. Because into visit recursively, we don't do anything fancy here. We're just forwarding everything to visit. So we don't have any logic for the recursion in here. This expects a visitor that's good for the variants. And our issue is that our overload will have n plus 1 arity, and we want to get it to n, and also have recursion. But this is exactly what Y Combinator does, because it takes something with arity n+1. It decrements the arity and allows us to recurse on it. So all of that means that when we want to create a recursive visitor, we need a y combinator over some very generic lambda here that takes self and a bunch of argument and returns explicitly by the template parameter we passed. And this will basically get rid of the self parameter in the interface and will give us a visitor that we can provide to stdvisit, which is wrapped behind visit recursively. So y combinator is doing the right thing here, reducing the arity and providing a way to recurse. And to create a visitor out of the lambdas, we can safely use our overload function. And I want to show you that overload resolution works well even if we have an extra parameter here. So in this very simple example, I just return false for int, char, and true for char, and I have an auto here. And when performing overload resolution, this extra parameter does not confuse the resolution. It's still going to find the best match between these two, even though A is implicitly convertible to int. So it still works. So if we can use overload for our function objects, we can simply initialize it inside the y combinator capture list by giving a name O, and then we perform the overload in here by forwarding all the function objects inside the function call. So right now we have the y combinator, the overload of all the lambdas, and please remember that the lambdas have the extra auto parameter because the user might want to use it to recurse. And everything is basically containing this perfect forwarding lambda that gives us the means to perform recursion with this self argument. So our goal is to call O, which is the overload we created, with the currently active variance alternatives. In the context of the lambda that we're passing to y combinator, so in the context of this lambda here, the argument pack XS represents exactly that, because the recursive visitor is going to be invoked through visit recursively. So let me explain that. When we call visit recursively, what we're going to pass is the result of this y combinator call. But y combinator will get rid of the self parameter from the interface for us. So all the variants are going to be forwarded into this XS argument pack. So we have a way of getting the variants that we want to visit inside the lambda that we provide to y combinator. The pack XS will represent the variants we want to visit upon. And the recursive visitor is going to be invoked through visit recursively. So the next step is basically saying, OK, we have the variants. So what we want to do is invoke the overload with something here that allows us to recurse, because this will be the self parameter in the user-provided lambdas. And then all the other parameters are actually the values that we might want to match with from the currently active variant alternatives. So we just forward the lambdas over here. Sorry, we just forward the variants over here. Is that clear? OK. So the last missing piece is this recurse here. So when we do this forwarding here, we're actually dealing with everything that's after the recurse. So all the values are being forwarded over here. But we'll still need to provide this thing here that magically allows you to recurse. So we need to fill up this question mark here with something that will allow us to recurse over and over on the same visitor. And this is the way you would use it. Again, it just takes a recursive branch of the variant and does the recursion for you. It doesn't need a visitor. It doesn't need an implementation detail. It just says, OK, please recurse on this alternative of my variant. And what can we use to invoke recursive visitor with variants? Yes, we can use visit recursively. We already have the thing that allows us to visit a recursive variant branch. So what we need to provide here is another generic lambda that takes a bunch of variants and then calls visit recursively with self, so with what the y combinator is providing as self, and forwards all the other variants as the arguments to visit recursively. So I will admit this is not easy to understand at first, but if you get your head around it, what this is conceptually doing is binding self as the first argument to visit recursively. And self, in this context, is the magic thing that the Y Combinator gives us to perform a recursive call onto this overloaded visitor. So what we're doing is exposing that self parameter here to this recurse parameter that's taken from the user-defined lambdas, and this will allow us to refer to the overload that we just created and recurse on top of it. And that's pretty much it. So this code is pretty much all forward and decl type. I wish we had a better way of binding things without potential runtime overhead or other issues. But this is all inlineable, all Constructor friendly. So this is the way to be as flexible as possible. So again, I want to reiterate, what we're doing here is capturing self by reference and binding it as the first argument of the recursive step. And the variants that we obtain from a recurse call are going to be forwarded to this recursively. And that's pretty much it. What we can do is try it out with make recursive visitor, and we just say we'll return int. We will ignore this auto here in the base case. In the recursive case, we will use it to perform the visitation again on the recursive part of the variant with the visitor that we just defined in place. And this works. You can try it out. You can see the generated assembly on Godbolt, and it just works. The last missing facility is the match recursively thing here, which performs in place recursive visitation. But since we have make recursive visitor, all we need to do is build a visitor and pass the variance to it immediately. So you can think of, like if you remember the match implementation, what we do is bind some variants, take some function objects, and then make an overload and visit. It is exactly the same thing, only that we change overload to make recursive visitor, and we change visit to visit recursively. So this is how match recursively works. Exactly the same idea as before. We take a bunch of variants, bind them, wait for some function objects. Then we overload the function objects by creating a recursive visitor. And then we call visit recursively on the newly created visitor. The only extra thing is that we need an explicit return type over here. Once we have that, we can finally visit a recursive variant in place doing something like this. So we can even say cout of match recursively of a variant, evaluate the variant, and then we're going to get the result in place, and it's going to be streamed out to the standard output. That's it. That's how we implement recursive variant visitation with lambdas. Now we have the final recap, and I'm exactly on time. I'm happy about that. So variants can be used to elegantly model recursive structures like JSON, AST, or lists, or whatever you think of. But since you need to keep their size fixed, you need some sort of layer of indirection. And that can be a unique pointer, std vector, any structure that works with incomplete types. And traditional recursive variant visitation using a struct is trivial. We didn't have to do anything. Like we didn't have to use Y Combinator or anything like that. We could just use this, which is great. But it suffers from the issues we discussed before. It is not really local, and it's harder to jump around in the source code when you're reading it. Therefore, what we want to do is create lambda-based recursive visitation. To do that, we need to remember that lambdas cannot recursively call themselves because it's impossible to refer to the current closure from the closure itself. And I think that this is something we need to address in the language. I would like to see a way of providing an identifier that allows us to refer to the current closure instance from the body itself. And recursion can be implemented by passing the lambda as one of its own arguments. And this, compared to something like std function, does not introduce any unnecessary runtime or memory overhead. And the Y Combinator higher order function generalizes this idea and minimizes the boilerplate, both in the implementation and on the user caller side. OK, now again, if you're visiting a recursive variant with very simple or one-off logic that you're not going to repeat throughout your code base, then the lambda-based approach is a good candidate. So if you're doing something simple that we are not going to reuse, consider using the lambda-based approach. But if the logic is complex and reusable, please use a struct. Please make a struct, give it a name, put it in a nice namespace, and use it throughout your code base. Please note that all the utilities that we covered in this talk can be used together harmoniously. Because if you remember the first implementation of the evaluator inside the struct, we actually used match inside one of the branches of the struct. So you can compose these things in order to avoid boilerplate where possible, but still retain the flexibility of structs with the extra overhead that come from them. So you can mix and match all the concepts. And all of these things can be adapted to optional as well, because conceptually, STD optional, boost optional is just a variant of something and nothing. So you can apply these techniques to optional. And as I said in the beginning, I'm actually working on a small library that works with any optional or variant implementation. And that's it. Thank you for coming. Hope it was interesting.